Hi, this is Sam Reynolds, and this is my presentation on calculating the circumference of Earth. The objective is to calculate the circumference of Earth using measured angles of shadows, and then compare that experimental value to the accepted value of Earth's circumference, which is 24,901 miles. So in order to do this calculation, it's very important that it be done on the spring equinox. The reason for this is because on the spring equinox, the sun is positioned directly over Earth's equator. So Earth's axis doesn't tilt towards or away from the sun. And additionally, what's very important is the sun rays are perfectly parallel to Earth's equator. This will simplify the geometry in calculating the circumference, as I will show in the next few slides. So if we were to take this circle to represent the Earth, and if we were to draw a sector of that circle from the center of the Earth to my backyard, and since it is the spring equinox, the sun's rays are perfectly parallel to the equator. This means that the angle of a shadow in my backyard is the same angle from the equator to my backyard. And then if we know the longitudinal length to the equator, which is the arc length, we can then use those two pieces of information to find the radius of Earth. And then from that, we can calculate the circumference of Earth. So if we look at that diagram one more time, and if we take that sector of that circle and move it over there, given the radius and the angle theta, using geometry, we can find the arc length s. And it's given by this relationship here, where the radius r is equal to s divided by theta. Additionally, the equation for the circumference is given by 2 pi r. And if we combine those two equations, we can get a final equation here to find the circumference of Earth. Here, s is denoted as the longitudinal length to the equator, and the angle of a shadow in radians is denoted by theta. This is my experimental setup. As you can see, there's nothing complicated to it. I have a stick cemented in concrete that's casting a shadow that I'm measuring with a string, and I'm measuring the angle with a protractor. Just a quick little note, this experiment was done on the spring equinox, which was March 19th of 2020, and it was done at solar noon. Solar noon on this day was at 12:58 p.m. It's not noon, 12 o'clock p.m., because solar noon is the midpoint between when the sun rises and when it sets. And on this day, it happened to be at 12:58 p.m. So this is my data. Unfortunately, on March 19th, it was quite overcast, so I was only able to get 3 good data sets, 3 good measurements. And you can see at the bottom, I highlighted one of them red. That was at 12:53 p.m. I highlighted it red because that was the one that was closest to solar noon. Unfortunately, I wasn't able to get a direct measurement due to cloud cover at 12:58 p.m., but 12:53 was close enough, and I got a measurement angle of 32.8 degrees. And then looking over to the right, I used Google Earth to find the perpendicular distance to the equator from my house, which was 2,306.59 miles. Then moving over to the analysis, I first converted the angles that were in degrees to radians, and then I also used the longitudinal distance to the equator plus the angle in that equation that I derived to then find the final answer for the circumference, my experimental value, which was 25,300 miles. This was only 400 miles off from the actual value of 24,900 miles. So it was very close to the actual value. The percent error was only 1.60%, so it was very low. I would have been happy with anything below 10%. So to get something this low was very good, and I was very pleased with that. So in conclusion, this project was very successful because I was able to calculate a value for the circumference within 2% of the accepted value. However, there was some possible sources of error. The first one was, as I mentioned, that it was quite overcast, so I wasn't able to get a measurement at solar noon. However, I think I was close enough, and I don't think a few minutes would change the angle that much. So the error with that was probably very low. I think a bigger source of error was the fact that I assumed the Earth was a perfect sphere. In all reality, it's not. It's what's called a oblate spheroid, which is just a fancy word for saying that it's a smushed sphere. Earth is actually thicker at its equator than it is at its poles, and that's due to Earth's rotation. So the calculation was not perfect due to that fact. However, it was still very close, and I'm happy with what my results were. Thank you for watching.